In this video, we'll cover the basics of carbon-13 NMR, just kind of go over an overview of how carbon-13 NMR could be useful when thinking about structural elucidation. I'll go over the key information that one gets in a typical 13 carbon NMR for proton decoupled spectra. We'll look at the number of signals, which will then equate to the number of non-equivalent sets of carbons in a structure. And then I'll go over some of the chemical shift aspects, which kind of give information about the neighboring environment around that carbon of interest. And I'll just go over a couple of examples that use these key pieces of information to try to determine what structure is most appropriate for the carbon-13 NMR shown. I have two problems that I will go over. So the NMR spectrum is related to the electromagnetic spectrum in terms of the type of radiation that is needed to get proton or even carbon spin states to have changes. And so we're looking here at the radio frequency region of the electromagnetic spectrum. Things like radio transmitters would be involved in that. And so what happens when you shine radiation in terms of radio frequency on a compound is that it begins to cause the spin states of, say, protons, or in this case, carbons, to align in one way or another. So without the pulse of radio frequency, the spin states are kind of oriented in all sorts of directions. When you pass the radiation through it, it aligns the spin states up either in the same or opposite directions, depending on sort of the neighboring environment. Here, we're going to be looking at proton decoupled carbon-13 NMR. So you're not going to get any splitting pattern based upon how many hydrogens are present. Okay, so carbon-13 NMR is a lot more simpler to understand and look at and interpret than a proton NMR for that reason, really. Some of the key information you can get from a carbon-13 NMR, the main one is you can determine how many non-equivalent sets of carbons are in the structure, and this will just correlate to the number of signals that you're seeing in the 13 carbon NMR. Carbons that are not interchangeable by symmetry elements, whether it's rotational or reflectional, will each produce a unique signal in the carbon-13 NMR. Carbons that are interchangeable by symmetry elements will produce a single signal for that set of interchangeable carbons. And so I've got some structures here, and we'll just use some colors to try to show you here that these two carbons are NMR equivalent because I can rotate about a sigma bond here, and they rotate into one another. And so that would be a case where we get equivalent sets of carbons there. But then if you go down here, that carbon is different from all the other carbons, so it would produce its own signal. And then as we just kind of walk along the backbone here, that carbon's different. For one, it's a CH2 group, not a CH or even a CH3 or even a C carbonyl. So it's just different, and it kind of passes that eye test right away. Here I have a carbonyl carbon, so that's going to be different and unique. And then lastly, on the far end, I've got a CH3 group, and that CH3 is different than these two CH3s because of its connectivity. It's next to a carbonyl, whereas these two are adjacent to a CH. So it just has a different environment altogether. Moving on to the next structure, one thing that I recognize here, there's a symmetry element present in the way that it's been drawn. And so we're going to start to see some duplicate here. So these two carbons are going to give one peak. Okay, so one signal for both of those because they're related by symmetry. And if we walk around the ring some more, This carbon is different than all the other ones. It's connected to no hydrogens, and it has all carbons attached. None of the other carbons can say that. But as you go around the ring, now we start to see that symmetry element. So the two halves of the ring are essentially symmetrical. So you're going to get two carbons here, but only one signal for those two. Furthermore, if we continue to do that around, those two carbons are equivalent. So just one signal for those two carbons. And then lastly, we've come to the other end of the molecule. That CH2 is different from all the other CH2 because it's just next to different carbons. And so those are all unequivalent in terms of the different colors. So for the first structure, I would see 5 signals because I have 5 unique sets of carbons in that structure. For the next compound, I would also have 5 signals for the same reason, but the carbon 13 NMR would look a lot different because the structure is different. There's not a carbonyl, it's got different electron environment. And so different spin states and chemical shifts. Moving on to the next structure, we have this benzene ring, and then there's an ethyl group attached to it, but there's still some symmetry about the ring there. And so let's work on the ring first. We've got this carbon's attached to an ethyl and no other carbon in the ring is, and then we start to see the symmetry on either side of that ring. And so we start to double up the number of carbons that give rise to a single signal. And lastly, we've got that carbon. And then the ethyl group, we've got a couple of signals that we'll see there. So we've got the CH2 here, and then we're going to have down the way from that another signal due to the CH3. Let's find the right there. So total here, I'm going to have 6 unique sets of carbons. So I'm going to have 6 unique signals in the carbon 13 NMR. Lastly, the final structure. There's symmetry about the middle of that. And so the two halves would be symmetrical with respect to those carbons. And so I'm just going to have 2 carbons in the structure, but I'd only see one signal. So it'd be useful to see a molecular formula so you can see the total number of carbons in the structure and then compare that to an NMR spectrum. You may or may not see the total number of carbons because on some of these we have to double up. More than one carbon give rise to one signal. Okay, so this would be 1 carbon 13 NMR signal, but 2 carbons total. And that's due to the symmetry element. So this is just a table I took from Klein's textbook, the 4th edition from Wiley, just showing sort of a general range where you kind of see your carbon 13 NMR chemical shifts for generic functional groups. So chemical shift, this is the resonant frequency of the nucleus relative to some standard in a magnetic field. And it's dependent on the shielding and de-shielding effects. So really what that's saying is the electron withdrawing and electron donating environment next to those carbons. It has very similar trends that one would see in the proton NMR as well, except that in a proton NMR, the scale doesn't go from 0 to 200. It goes to about 0 to 12 or so. And so it's just on a different time, on a different chemical shift scale, but the trends are very similar, meaning that, an alkane carbon is as far right as almost it's going to get. So hydrogen that would be attached to that carbon would show up in a very similar spot in terms of being further to the right. And so when we talk about upfield and downfield, the more right you go, this is more upfield. And the more left is more downfield. So you can say that an aromatic carbon is more downfield with respect to an alkane carbon. Okay. Why? Because it's got more electron withdrawing properties around it. So it de-shields it. And so the more downfield, the more de-shielded. With respect to other carbons that wouldn't be as far to the left. Okay. Once again, these are just tables that one can look up and find just ranges of where you'd see typical chemical shifts at. I'm not going to go through all these. These are tables that one could look up or find other tables that are similar. So what I want to do is just look at a couple spectra here. I've got A, B, C, and D as options for the structure responsible for the carbon 13 NMR shown here. So if we just kind of dissect each structure like we did with the previous slide, we'll see here that, okay, I've got a carbon there. I've got another carbon there. I've got another carbon here. Another one here. Here. I'm needing more colors here because I'm running out of room here in terms of the symmetry, in terms of how many colors I was using, but we've got no symmetry present. And so there's going to be just a single peak for all of these. Okay, so I see how many colors I have. 1, 2, 3, 4, 5, 6, 7, 8. I see 8 unique carbons, so I would expect 8 peaks. And looking at this carbon 13 NMR, I have 1, 2, 3, 4, and 5. And so A cannot be the correct structure for this carbon 13 NMR. If I go to B, B has some symmetry involved. And so I've got 5 unique carbons. So I should see 5 peaks. So this could be a possibility. Let's see what the other structures show us as well. And so let's go ahead and kind of do the same thing for the other ones. And I've got 6 unique carbons, so I would see 6 peaks. Sometimes peaks in the NMRs can overlap with other peaks. In this case, I don't have that happening. I've labeled A, B, C, D, and E peaks for you. The last structure has a lot of symmetry present. And so looking at that, these methyl groups are all equivalent. And then we're going to have the carbons that are attached to the methyl groups. Those are all interchangeable to look like the others, either by reflection or rotation, about some symmetry axis. And then I've also got these 3 carbons on the ring that are attached to hydrogens. They're kind of equally spaced around. So those are all interchangeable as well. So I've got 3 peaks that I would see and the carbon-13 NMR for that compound. So we can rule out now C and D, and in fact, B is the compound responsible for this carbon-13 NMR. Okay, so the most downfield peak E is going to be in your aromatic region. So it's going to be a carbon that's part of the aromatic ring and also attached to another electron withdrawing group. So if you look here, these are all aromatic regions. These are all kind of where you see normal alkenes here, but then your aromatic compounds have a range somewhere in here. If we go back to a table, you can kind of see the range for the aromatic ring is somewhere within where we're seeing it show up for all peaks B, C, D, and E. The one that's next to that oxygen is going to be peak E. And so then you can start to assign those carbons appropriately. Over here, I've got a carbon that's not in an aromatic region, but it's still next to something electron withdrawing because it's not over here at the normal alkyl range. So this is a carbon next to an oxygen, maybe of an ether. And so I think A is there. So you can see the influence of the electron environment has on its chemical shift. And so I'm labeling the wrong structure here. Sorry. Let's go back and do structure B. So we said E is here. This is A. And if we look at the other peaks, you can see the ratio of those heights is almost 2 to 1. And so the one that's next to an electron withdrawing group, I believe, is going to be either one of these two, or it could be one of, one of these two, or one of these two, being D and or B respectively. So I do know here that this one is going to be C, because you can see the height of the peak relative to B and C is only half. And so there's 2 carbons giving rise to one of these peaks. That's a singlet instead of just one. And so you can see the peak height ratio being influenced by that. And so I believe here this is going to be B, and this will be D, respectfully. So that's how you can kind of use the carbon NMR to help you decide what structure you may or may not have. So I have one more to practice here. I've got how many peaks? Let's decide. I've got 1, 2, 3, 4, 5, and let's say, I think I have 6 peaks there. So one thing to notice on this carbon-13 NMR is it looks very similar to this one in terms of these 4 peaks. We kind of see them kind of showing up again, but now I've got this extra peak here. And so that's going to lead me to believe that we're going to have some sort of a alkyl-like carbon that's not next to an oxygen, but next to another alkyl carbon. If we look here at what we've already decided, A has 8 peaks, B has 5, which we've assigned to this NMR, D has 3 peaks, so that wouldn't work. It looks like the best possibility is going to be structure C here. So just kind of labeling this for you, A, then I have B. Now I've got a bromine on here. So this one's going to be F. And then this, I believe, is E and D. So I'd have to check on E and D, but the lone pair on the oxygen can donate into the ring a little bit better than the bromine. So it makes the position at D a little bit more electron delta minus because of resonance. So I think that that is properly assigned. But the point is 6 peaks because I have 6 unique carbons in the NMR. And that's really the best information you're getting from the carbon-13 NMR for this type. There are other types of carbon-13 NMRs that we're not talking about, including depth NMRs, which shows peaks above or below the chemical shift axis as being up or down based upon whether they're CHs, CH2s, or CH3 carbons. Okay, but those are outside the scope of this video. Okay, so hopefully that helps, and thank you for watching, and I hope you enjoyed. Goodbye.